Hello class, you are welcome back to session 3 or part 3 of our journey or discussion on calculus. So if you are new here, I have given the links of the previous video that we have done so far in the description section of this video. You can check and then watch them so that you can also build an understanding from there up to this point. Okay, better so continue watching this video so that you go back to or so that you get it right other way. So make sure to like this video and subscribe so that we can get more engagement. Like and subscribe. Is that okay? So let's go through real quick in this case. So we are looking at higher derivative, and as we journey on, we're going to look at other rules of differentiation. So for now, we are looking at higher derivative in this case. So when it comes to higher derivatives of a function, this is what we are saying. So for what we have been discussing on is differentiation for the first time. When you differentiate the function for the first time, and at the same time we differentiate the function for the first time, we call it what? Dy over dx. We call it dy over dx. For the first time, it's called what? So any function that is differentiate for the first time is called dy over dx. So when you also continue to differentiate the function again after the first differential, we call the second what? Derivative. We call the second what? Derivative. So the first differential becomes what? The first derivative. So here is the first derivative. First derivative. Alright. So when I differentiate the function the second time, we call the second derivative, and that one we call it d squared dy over what? Ds squared, and that's called the second what? Derivative. That's how we write it when you are differentiating the y part of the quantity in this case. When you differentiate for the third time, we call it the cube y over the s cube, and that's called your third derivative. When you differentiate it for the fourth time, it becomes what? D to the power of 4 y, then the x to the power of what? 4, and that becomes what? Your fourth derivative. So you can continue and on and on and on. So whatever you want to differentiate until you get 0, fine. It ends there. So that becomes the higher derivative of what? A function. So higher derivative of a function here, where find derivative of function more than what? Once. Where you find the derivative of function or you differentiate the function more than once. That's what we call derivative. So for the first time, we call dy over ds. For the second time, we call d squared y over ds squared. For the third time, we call d cube y over ds squared. And for the fourth y over what? Ds fourth. That's the fourth square or to the power of 4. It can go on and on and on in that case. So that's the whole concept about the higher derivative. And then also, if they are being presented in a form, let's say f of x, in this case you're going to write as this: f prime of what? X. So that's the first derivative. Just f prime of the same thing I do over ds. And then here is going to be f prime of what? X. That's double prime. Here is going to be what? F prime triple prime of x. Here is going to be f prime fourth time of what? X. And the same thing as what? F d to the power of 4y over dx to the power of what? 4. So either you see this or you see this, they are the same. So at any point where you are dealing with these expressions, remember these symbols or these signs are what? The same. So let's take note of them. They are equivalent in terms of their relation. So let's take note of that. Hope that is clear. So that's higher derivative. General, that's higher derivative. So let's take a function like if I have y to be equal to, let's say, s to the power of 6 plus, let's say, 5s squared. Sorry, 5 to the power of 5 minus, let's say, 4s to the power of 4 plus, let's say, 3 to the power of 2. So for the first time, it becomes what? Your dy over what? Dx, and that's going to give me what? 6x to the power of 5 plus So 5 multiplied by 5 will give me what? 25. So 25 to the power x to the power of what? 4, right? Minus 16 to the power of 3 plus 6x. I hope that's clear. So that's for the first time. So for the second time, it becomes what? D squared y over what? Dx squared. And that is going to be from the first derivative. It's going to be, so you multiply 5 by the 6, it's going to be what? 30. And you subtract 1 from the 5, it's going to be what? X to the power of what? 4. I hope that's clear, right? Plus, you also multiply the 4 by the 25, it's going to give you what? 100. And subtract 1 from the 4, it's going to give you x to the power of what? 3. Minus, and you do same. 3 multiplied by 16 is going to give me what? 48. Now subtract 1 from the 3, it's going to give me x to the power of 2. Plus, and here to multiply the 1 by the 6 is going to give me what? 6. And I subtract 1 from the power of what? X. That's going to give me what? 0. So x to the power of 0 is what? 1. So we're going to get expression like 30 x to the power of 4 plus 100 to the power of s cubed minus 48 s squared plus 6. I hope that's clear, right? So for the third time, it becomes d cube y over dx cube, and that's going to give me, so here too I'll multiply the 4, the same differential. You multiply the 4 by the 30, it's going to give me what? 120. Now subtract 1 from the 4, going to x to the power of 3. I hope that is clear. Then here I'll also multiply what? 3 by 100, it's going to give me plus what? 300. Now subtract 1 from the 3, going to give me x to the power of 2. I believe that is clear. Minus, I'll multiply the 2 by the 40, it's going to give me what? 96. Okay. And then I'll subtract 1 from the 2, we're going to get what? X. Differential of constant is going to get me what? 0. So plus 0. That is all. So plus 0. For the fourth time, y over dx to the power of 4. Here too I'll multiply what? The 3 by 120, it's going to get me 360. Then I'll subtract 1 from the 3, it's going to get me what? To the power of 2. Now I'll multiply the 2 by 300, going to give me what? 600. Now subtract 1, going to give me x, right? Now differentiate 96x, going to give me what? 96. So actually, if you got the concept right, differentiation becomes like you are playing with maths. You easily get it right. It becomes very simple for you. So you just play with it and then you are good to go. Once you understand the principle, just work it straight away and you are good to what? Go. So that is, and you can go on and on to differentiate till even the whole expression becomes what? 0. And that's where it will end there. I hope that's clear. So that's higher derivative when it comes to differentiation. So let's take note of that. So let's move on to, so you can actually create your own example and even differentiate till all the function remains 0. Then you can tell us that that's in that case. So let's continue to talk about other rules that we need to know, like chain rule and then implicit differentiation. So let's see how we also want to take those ones in that case. So let's look at chain rule as the next rule for differentiation. Now with the chain rule, let's say if I have, or let's say y, right, is a function of u, so it's going to be y is equal to what? U. And at the same time, u is also the function of what? X. Then we can conclude that, therefore we can say that then y can also be a function of s, or s can be a function of what? Y. I believe that is clear. The idea of trying to establish here is that we are saying that y is a function of what? U. Alright? And at the same time, u is a function of what? X. Therefore, we can conclude that if y is equal to u and u is equal to x, then we can say that automatically y is also going to be what? X. Y is going to equal to what? X. Now, stay here careful. When it comes to chain rule, after differential, it's going to result in what? Multiplication. Get this right. When it comes to chain rule, after their differential, it's going to result in what? Multiplication. So this is what you're going to do. First of all, find the differential of y is equal to u, and also find the differential of y is, so u is equal to x, and also find the differential of what? Y is equal to x. After that, you multiply the differential of y is equal to x by u is equal to x, and you equate to the differential of y is equal to what? X. Get this right. First thing, we are saying that the differential of our chain rule is going to result in multiplication. Okay, and we have established that y is a function of u, and at the same time u is also a function of what, x. Then we can conclude that y is also a function of what, x. So here, get it right. The idea we're trying to put across here is that after getting these expressions, you first find the differential of y is equal to u, and also find the differential of u is equal to x. You also find the differential of y is equal to what, x. After that, the product of the differential of y is equal to x and u is equal to x is going to be equated to the differential of y is equal to what, x. I believe that is clear. So here's what you're going to do. I'll first start with y is equal to u. So I can say that with this going to be dy over what, du. I'm only interested in the expression that comes before the equal sign, this expression. I'm just interested in these values, y, u, and then the y here. The x, that's not my thing, but I'm differentiating with respect to various for quantity that they have in each case. So that's for the y is equal to u. Let's come back to the u square. So you're going to go what, du over what, dx. And then here too, I can say that here is also what, dy over what, dx. So therefore, we are saying that chain rule result multiplication. They're going to multiply, take the product of what, the differential of this, and that was what, this and this, and you equate to what, the differential of y is equal to x. So it's going to be my dy over dx, which is going to be the product of my dy over du multiplied by my du over what, and dx, and that will result to your chain rule. So always chain rule, your dy over dx is going to be your dy over du multiplied by your du over dx. So that is the concept about chain rule. So let's take an example. Example 1. If y is equal to, say, 3x plus 2 all to the power of 5. Chain rule. This is how chain rule comes in. All that you're going to say here is that let 3x plus 2 be equal to u. So we can say that, therefore we can conclude that y is equal to what, u to the power of what, 5. I hope that is clear, right? Because we have substituted 3x plus 2 in place of what? We have substituted u in place of 3x plus what, 2. And that's going to result in y is equal to u to the power of what, 5. I hope that is clear, right? So once you're able to get this, then you differentiate each expression individually here. So therefore I can say that here, my dy over du is going to be here the normal expression or normal differentiation. The 5 will multiply the u, so it's going to be what, 5 u, and I'll subtract 1 from the 5, so going to be what, to the power of 4. Then I also differentiate this expression, 3x plus 2 is equal to u. So that one too, I can say that here, so let me bring it here, 3x plus 2 is equal to u. So I can say that here, or let me write in this way so that you appreciate it more better. So I can say that here u is equal to 3x plus 2. So therefore I can say that du dx is going to give me what, 3. Accepted. For 3s, when I differentiate 3, I'm going to get 3. Differential of a constant is going to give 0, so it becomes what, 3. So therefore I can say that my dy over dx from this I'm differentiating is going to be my dy over du multiplied by my du over what, dx. Hope that is clear. So here let's see. So now I know my dy over dx to be what, 5u to the power of 4 multiplying by, I know du over dx to be what, 3. So it's going to be 15. 3 multiplied by going to be what, 15. But I know u to be what, 15u to the power of what, 4. But I know u to be 3x plus what, 2. So to the power of what, 4. And then that is going to be my differential. So therefore dy over dx is equal to 15 into bracket 3x plus 2 all to the power of what? 4. I believe that is clear. So that is the chain rule approach when it comes to differentiation. That's the chain rule approach that it uses. So let's take note of that. Or you can have other ways that you can also work. If you want to use a normal rule of differentiation, you can also work in this way. So let's see how I also go by that approach too. Or if you want to use the normal rule for differentiation, this is how you can also go about it. So here straight up we can say that your dy over the x is going to be, so this is what you're going to do. You first of all multiply the normal differentiation rule. First of all multiply what? The 5 by the whole expression 3x plus 2. So it's going to be what? 5 into bracket 3x plus 2. Okay, and you repeat it with the power of 5 and subtract 1 from here. After that, you differentiate the expression within the bracket individually. So that's going to be what? When I differentiate 3, it's going to be what? 3. When I differentiate the constant, it's going to be what? 0. So it's going to be more like this. Put it in this way. Plus 0. Remember, we said chain rule results in what? Multiplication. So therefore, I can say that my dy over dx is going to be 15, because 3 going to multiply with 5, going to 15, right? Into bracket 3x plus 2 all to the power of 4. It's the same thing as this. Simple. So if you want to use the normal rule of differentiation, first we differentiate the power. So the power is going to multiply the whole expression of 3x plus 2. Alright, after that you differentiate the term in the bracket, which is 3x plus 2. When I differentiate 3x, I'm going to get 3. And if you 2, I'm going to get what? 0. So it becomes 3 plus 0. Alright, and after that, I'll repeat the 3x plus 2 with the power of 1 and subtract 1 from the 5. And I'm going to get what? 3x plus 2 to the power of 4. Now I'll multiply the 3 by 2, I'm going to get 15. And that will result in this. It's the same thing as using the chain rule. So which of them that you think is safer and faster, you can work with it, and that's going to be the way out. Like, let's try this. If I have y to be equal to, let's say, 2x plus 1 all to the power of, let's say, 8. You can use chain rule. I can also use normal differentiation. With the normal differentiation, I can say that here dy over dx is going to be the 8, going to multiply the whole expression, right? And I'll differentiate the terms in the bracket individually. So it's going to be after multiplying the 8 by the whole expression of 2x plus 1, I'll differentiate the individual terms here. So when I differentiate 2, I'm going to get what? 2. Differentiate the 1, I'm going to get what? Plus what? 0. So plus 0. Alright, and I'll repeat the expression 2x plus 1 to the power of 8, and I'll subtract 1 from here. So therefore I can say that my dy over dx is going to be 8 multiplied by, it's going to give me what? 16 into bracket 2x plus 1 all to the power of what? 7. Anyone also use the chain rule, you're going to get the same answer as this. And that is how the chain rule and the normal rule of differentiation apply. So if you get any expression like this or function like this, first differentiate the power, multiply the power by the whole expression, differentiate individual terms within the expression, repeat the expression again with the original power and subtract 1 from the original power. And that is going, at the end of the day, when you simplify it further, that is going to be your result in that case. So that is how it works. So make sure to get it right and apply. It can help you, it can speed up the time when you are far behind time and you don't want to use the rules. You can still use, the formulas for the various cases. You can still use the normal rule and you are good to go. So let's take note of that. So let's move on to talk about the implicit function, where we have two or more expressions or two or more variables at the same time, whether they are multiplication, division, or subtraction, anything of that we're going to look out for in this case. So let's see how we dive deeper to those aspects too. So we're going to talk about implicit function. It's implicit but not implication, implicit function. So let's take note of that. So let's look at the implicit function of differentiation. So far what we have been looking at for is where if I have, let's say, y is equal to, let's say, 2x squared plus, let's say, x plus, let's say, 2. In this case, we call this function as being what? In an explicit form. Why? Because the variable involved here is just y on one side and then x on the other side. But hey, there are some certain situations where you may have, let's say, y to be equal to, let's say, xy plus, let's say, y square. In this case, we call this function as being what? An explicit, because at this stage it becomes very difficult for you to separate either y or x apart. And for you to do that, you need to differentiate so that you know whether it's going to result in addition or subtraction or even multiplication. So when you see an expression of this form, we call them an implicit what? Function. And expression of this form are called what? Explicit what? Function. Explicit. And this expression is called an implicit what? Function. Implicit function. So expression where you have two or more variables involving, where you cannot separate them at the same time. So we call what? An implicit what? Function. Implicit. There's no y, sorry. Implicit what? Function. Implicit function. Implicit what? Function. An expression of the form 2x squared, where we have just two variables and one variable stand on one side and another variable stand on the other side, we call it explicit function. But where you have two variables in which one variable stands on the other side, you have another variable, or two variables will stand on another side with different variables, we call them what? An implicit what? Function. And to separate them, you need to use an approach of differentiation. We're going to use the implicit function approach of differentiation to differentiate such expression or such function so that we can know the change that is existing between these two quantities in that case. So that is the concept of the implicit function. And how do you undertake this expression? I'll first of all start with the example I've given here. Y is equal to xy plus what? Y squared. How do you differentiate this kind of what? Expression? It's important that you know how you differentiate it, right? So here when I differentiate, remember I'm differentiating with respect to what? S, so it becomes what? Dy over dx. Is that okay? Dy over dx. And that is going to be, so here to, if you remember the product rule, you hold the x, you differentiate the y. After that you add, then you come and hold the y and differentiate the x. So that is the whole approach. Actually we have dealt with those ones, but just that you want to revise ourselves, or we want to remind ourselves what we have done. So here I'll hold the x and I'll differentiate the y. So when I hold the x, I'll differentiate the y, it becomes what? Dy over what? Dx. Because we are differentiating with respect to what? X. So dy over dx. Plus, and here too I'll come and hold the y and I differentiate the x. So when I hold the y and I differentiate the x, we're going to get what? 1. Going to 1. I hope that is clear. Plus, then here is what? Y squared. So what will I do? All that I will do here is what? Normal differentiate. The two can multiply the coefficient of y, which is what? 1. So it becomes what? 2y. And then, when you differentiate the y, you're going to get what? So you're going to be left with 2, right? After you subtract 1 from it, you're going to get 1, which is what? Y. When you differentiate the y, you're going to get what? Dy over what? Ds. So note that when you differentiate the y, irrespective of what the power or the exponent, anytime you differentiate the y, you're going to get dy over dx. If it is respect to x, then it's dy over what? Dx. I hope that is clear. If you respect to x, then it's dy over dx. But if respect to any other quantity, it becomes dy over such quantity. I hope that is clear. So irrespective of the power, it becomes dy over dx. After that, you go by the normal differentiation before you deal with the power. So here, the first thing I need to write even is my dy over dx before I even deal with the power. So the power is going to multiply the coefficient of y. That's going to give me what? 2, and I'll subtract 1 from the 2. So I'm left with what? 1. So it becomes what? 2y dy over dx. I hope that is clear. So once you're able to get this, then I'll make dy over dx the subject in this case. So here it's going to be, what I'll do here is to group them. Is that okay? So here, that's what I will do. I'll group them. So I can say that I have my dy over dx here. Is that okay? Minus my x dy over dx minus my 2y over dx. Hope that's clear. Right, then after that I will equate to what? Y. I'm going to do factorization. Is that okay? So here I can say that my dy over dx is going to be 1 minus x minus 2y. Hope that's clear. And that's going to give me what? Y. So therefore I can say that my dy over dx is going to be y all over 1 minus x minus what? 2y in this case, and you are done. So that's going to be your dy over dx. Then you are done. So that is the implicit function when it comes to differentiation. So let's take note of that. Let's try this one out. If I have this, let's work this one out. If I have, let's say, x cubed plus what? Y cubed plus 3x y squared is equal to 8. Here, as to differentiate this function, how are you going to differentiate that? So here x is standing alone, y is standing alone, so it's only here going to use our product rule. And when you differentiate the constant, you're going to get what? 0. So here, differentiation of x is going to give me what? 3x squared. It is only y, whether you differentiate, you're going to get dy over what? Dx. So it's going to give me 3y squared dy over dx. I hope you are okay with that. Yeah. Plus, so here too, this is what I will do. I'll bring the 3 out and I'll differentiate the x and then the y squared in this case. So it's going to be, so I'll hold the x and I'll differentiate the y squared. So it's going to be what? X. So here it's going to be into bracket 2y dy over dx. Is that okay? Plus, then here too, I'll come and hold the y square and I'll differentiate toward the x, which is going to be what? 1. Then I have, and it's equal to what? 8. I believe that is clear. I hope that is clear. So at this stage here, it becomes what? 3x squared plus 3y squared dy over dx. Now let's expand the bracket here. So let us expand the bracket, or let's do with it first before we expand. So it becomes what? Remember, when I differentiate constant, it's going to be 0. So here should be 0, not 8. Take note. 0. So here is going to be 2xy dy over dx. Okay. Plus y squared is equal to 0. So here it becomes 3x squared plus 3y squared dy over dx plus, so let's expand it. So it becomes what? 6xy dy over dx plus 3y squared, that's equal to 0. So here I want to make dy over dx the subject, so I'll group them on one stage. So here I can say that here can have my dy over dx into brackets. I have here to go what? 3y squared plus what? 6xy. Alright, and that is going to be equal to, so here is going to be negative what? 3x squared negative 3x squared negative 3y squared. I hope that's clear. So once I get to this, I'll divide both sides by 3y squared 6xy. Divide both sides by 3y squared plus 6xy. So once I get to this stage, I can write this. Okay, so remember, this 3 can cancel this 3. So at the end of the day, I can say that my dy over dx is going to be negative bracket x squared plus y squared all over y into bracket y plus what? 2x. And that's going to be my answer in that case. So let's take note of that. So that is an implicit function. Actually, implicit function will consist of what? where you have one function on one side, we have one variable on one side, you have two variables also attached together on another side, where it becomes very difficult to separate them. Before you can do so, unless you differentiate, apply the implicit differentiation rule to differentiate and separate them. Like where you have one variable standing on one side, another variable standing on the other side, we call them what such function as what being an explicit. But the opposite is called the implicit. So that is the implicit rule when it comes to differentiation. So this is where we bring an end to our presentation on part 3 or section 3 of our calculus. So in our next section, we are going to look at section 4, where we discuss the maxima and the minima of a differentiation of what a function and other things that you need to know. So I'll see you in that section. For now, bye bye. But make sure to like and subscribe. Make sure to like and subscribe. So I'll see you. Bye bye.